Good morning. Hello. Uh, Welcome to the first session in November for DBA Fundamentals. Today we have Mark Wilkinson with indexing from the ground up. But first, I need to talk to you about a few other things. I'll try to make it quick. Our one of our sponsors, Century One, is a great company, got great products, and they help pay for all of this. So please go and visit these links and tell them that DPA Fundamentals sent you. If they ask how you found anything about it, they've got great downloads. They've got books like you wouldn't believe, read books. Well, read books is another thing, but PDFs that are great information. You can get great videos besides the ones we do, obviously, and pass. There's great articles. You can get free tools. The Plan Explorer is worth. I mean, if you haven't never tried it, go get the Plan Explorer from Century One. It's like 5 or 6 times better than the regular Microsoft Plan Explorer. Fantastic. Okay. DB Watch is one of our other sponsors. They're actually going to have a session for us in December the 18th. Please tune in for that. They're going to be able to talk a little bit more about their product and also give us a really good T-SQL presentation. These are the people that work for us that help bring you this: Steve Cantrell, myself, Glenda Gable, Kevin Wilkie, and Shane O'Neill. PASS has tons of virtual groups. We're having less than we used to. They're trying to spread out to practically every topic in the world, but we have one for practically every major language and practically every major topic. Go try that out. Join any groups that you feel comfortable with. We focus on fundamental aspects of DBAs, but there's lots of other great options. And I just ended it a little bit quickly, but basically this session will be recorded and it'll be on our YouTube site, DBA FunTube, in about a day or so, maybe even earlier. I'm going to go ahead and turn over the session to Mark. Mark is DBA from Raleigh, North Carolina, and he loves playing with being around his kids, and I understand that, and he loves dealing with SQL and solving problems. And he's going to talk to you today about indexing from the ground up. And this is a great, I mean, really, you need to listen to this because these are the type of things that help you with index tuning further on down the road. He's told me a little bit about what he's going to do. So listen to it. Let me turn you over to Mark, and he'll probably have some more introductions of himself. Let's see. Okay, Mark, there you go.
All right, let me just share my screen here. All right, is my screen visible?
Looks good to me.
All right. All right, well, this is indexing from the ground up. I am Mark Wilkinson. Just a little bit about me. I'm a father of 4. I live in Raleigh. I actually live just outside of Raleigh, but nobody seems to know where Garner is. So I just tell everybody Raleigh, but I actually live a little bit south of Raleigh. I wear a quote unquote sick calculator watch. That's what somebody told me once. I like beer, performance tuning, monitoring. I'm a developer at heart, so I love PowerShell, Python, and Go. A huge fan of dumb internet memes. And I manage a DBA team at Channel Advisor in Morrisville, North Carolina. All right, so today, the agenda, we're going to go a little bit into index internals, We're going to talk about heaps and clustered and non-clustered indexes. We'll go into some general design considerations and then index design anti-patterns. So we're not going to go into any of the newer index types, like the column store indexes. We're not going to talk about in-memory technologies. We're just talking about the basic clustered and non-clustered indexes and a little bit about heaps. And when I say internals, we're going to start with talking about how SQL actually stores data. It's not something you absolutely need to know, but I find that it helps a lot of people think about indexes in a more useful way. And if anybody has any questions throughout, oh, actually, I see a question here. Is it a Casio? Yes, it is. $15 on Amazon. They still sell them. All right, so we'll get started here on page types and storage, and just how SQL stores data. All right, so this is a simple representation of how an index looks in SQL. It's a collection of linked pages. You'll typically have a root page, some intermediate pages, and some leaf pages. When I refer to a page is an 8K block of data. Pages are further sorted into something called an extent. An extent is simply just 8K pages. For the most part, we're not going to talk about extents. There is one specific place where I'm going to talk about them in something called an IM page, which we'll get to. All you need to know is that it's a way that SQL, stores collections of pages. So as I just said, there's 3 levels of pages here: the root, intermediate, and leaf. The root and intermediate are what I refer to as navigation pages. It tells SQL Server how to get to the data that it needs. And then down here at the bottom, the leaf level is where the actual data lives. So there's some differences in what is on the leaf level when you're talking about non-clustered and clustered indexes, which we'll talk about here. So just a few notes on page types. You're only ever going to have one root page. So back to this little diagram here, this top page here, you're only ever going to have one of these. You're only ever going to have one leaf level. So this here at the bottom, there's only going to be one level of leaf pages. I specifically call that out because you can have multiple intermediate levels. So these pages here, if it's a large table with a lot of records, you might have 2 levels, 2 levels of intermediate pages, or 3 levels. New intermediate levels are created whenever the root page can no longer store one entry for every intermediate page. And the intermediate pages themselves are first created when the root page can't store an entry for every leaf page. What that means is that for every single one of these leaf pages, each of these have a page ID. There has to be enough room on this root page to store an entry for each one of these pages. And if it can't fit on a single root page, it'll create an intermediate level to kind of break the data up. So this page will reference these 2 pages. This page will reference these 2 pages, and then the root page only has to reference these 2 pages instead of all of these down here in the leaf. So if we were to get to a point where there were so many intermediate pages that the root page couldn't reference each one individually, it would just break it out into another level of intermediate pages. On some of our largest tables in my environment, I think the deepest index I've seen, the most layers, is 4 levels. So a root, 2 intermediate, and a leaf. Is there any questions about that? I see we got one here.
Yeah,
oh,
you see it.
Yeah.
Just how many intermediate pages can SQL Server create? Is there a specific algorithms running behind the scenes to calculate that?
As far as specific algorithms, I'm not sure. And I think once we look at the page, we're going to look at these pages, and I'm going to show you exactly what's on the pages. It'll make a little bit more sense to you. There's nothing complicated about the pages. It's like the root page, it has some header information, and then it literally just has a list of pages on it. So there's a limited amount of space because again, we're dealing with these 8K pages. So if the root page runs out of space within that 8K to reference every one of these intermediate pages, or every one of these leaf pages rather, it'll create an intermediate level. So there's no fancy algorithms or anything involved in that. It's just, is there enough room on this page to reference everything in the layer below it? And how many intermediate pages can SQL Server create? I don't know that there's a limit. I don't know that there's a limit that would ever be approached, because it would basically it would start creating more and more levels to store more data. A couple more here. Can you see them in DMVs? You can see things in DMVs, which when we get to the demo portion of this, I'll show you some DMVs where you can actually see the all the indexes associated with a given table, and then some DBCC commands you can use to look at the contents of a page, and that's part of this whole beginning part of this talk, is to look at that so you can get a better understanding of how these things are structured. One IAM per page per object was another question. We're going to go into that. And then what is a row identifier? We're going to go into that when we talk about heaps. All right, so let's moving on here. I think I covered everything here. This big bold thing at the bottom is important for understanding the depth of an index, how many levels it is, so that every single leaf level page must be referenced by a root or intermediate page. So somebody was asking about IAM pages. Index allocation map pages, it tracks the pages in mixed extents and the uniform extents the object data is stored in. So it basically tells SQL what pages it needs to look at to get the data for a given index. Any single IAM page is only going to be able to track 4 gigs of data. So you're going to have multiple IAM pages per object if your objects are larger than 4 gigabytes. There's also separate IAM pages per index and per partition. And then further, there's separate IAM pages for in-row data, row overflow data, and lob data. Lob data being like, text. And if an IAM page needs to track more than 4 gigs of space, it creates another page, and then they're chained together. They're linked. And when you actually interrogate the page using DBCC page, it will tell you what the next IAM page is, and so on and so forth. So there's a linking created there, and that's called an IAM chain. All right, so we're going to get into the actual structure of the indexes. I'm gonna give you some kind of general overview of these things, and then we're going to go into the demos, and we'll see a little bit more detail. So a clustered index is the data. When I say it is the data, if we go back to this diagram here, when you have a table that has no indexes on it and you create a clustered index, the table and the clustered index become the same thing. There's no difference. The table data is stored in the clustered index and nowhere else. And it's all stored at that bottom level there at the leaf layer. So as soon as you create a clustered index, all of the data in the table, every single column, gets stuffed into these leaf level pages down at the bottom. It physically sorts the data. The root and intermediate pages, and this is an important point to remember. And I'm asking you guys to kind of hold on to information for a while in this presentation, because near the end it all comes together and makes sense. But the root and intermediate pages, they store the clustering key and the page ID for the related leaf pages. So what that means is that if you have a clustered index, and it's what's called like a compound key that has multiple columns, like let's say you've got a table with 6 columns in it, and your clustered index is on 3 of those, those root and intermediate pages are going to have those keys listed on them. So the wider the key, the less records you can actually fit on the root and intermediate pages, which could cause your index to grow as far as the different levels go. So you might have more and more intermediate page levels being generated if you've got a really large clustered index key. And we'll talk about why that's important. But for now, just remember that those navigation pages, the root and intermediate pages, actually have the clustered index key on them. And then, as I said, the leaf pages store all of the data. The leaf pages can be thought of as the table itself.
You have a question. Is the clustering key effectively the same as the hash would be in a parallel processing environment, for instance, a data warehouse?
I can honestly say I don't know. I have never worked in a parallel processing environment. Hash. Yeah, I'm not sure how to answer that question. I'm sorry. The clustered index, if it'll help, the clustered index key is just how SQL sorts the data that's in the table, and the order in which it looks that data up, if that helps. So I'm going to show you an example here, and maybe this will even help with that question. We've got a table that just holds a list of people in it, and we know the ID of a person, and we want to look that person up. The ID that we know here is 126. So here we've got a representation of some pages. This is a very simplistic representation, but we've got page 1 here, which is the root page. Got page 3, which is one of the intermediate pages, and then we've got page 12 here, which is one of the leaf level pages or the data page. As you can see, this table here, it has an ID, it has a person's first name, it has their age, and then a number, which I don't remember what this was supposed to be, but some sort of data is stored about this person. Maybe if their account is active or something like that, you could think of it that way. But yeah, so we've got 4 columns in this table. So we want to look up the person whose ID is 126. So what we do is we start at the root level, and as you can see, we've got 100, 200, 300, 400, 500. So all of the records are not represented. Like we've got 122 here. That's not listed here. What SQL does is it looks at these values and says, if we have an ID between 100 and 200, not including 200, we go to page 3. If it's between 200 and 300, we go to page 4, and so on and so forth. So for our lookup, we're looking for 126, which will be between these two. It'll go to page 3. It'll hop over to page 3. It sees that 126 is between 121 and 131. So to go to page 12, hop over to page 12, and we get to our record here at the bottom. So each of these pages here in like the navigation layer stores the page, the clustered index key. The lowest clustered index key that's on the page and the page ID. So if we looked at page 12 here, notice how it's got 121 through 126. If we were to look at 14, it would start with 131 and go all the way up to 140. So in these layers here, it stores the lowest ID that's on the page and the page ID. And we'll look at this with some demos as well to make it make a little bit more sense. And now is the time for that. So let me switch over to a demo here. All right. Okay, so, well, as you can tell, I present this at SQL Saturdays, but we've got a demo database here called SQL Saturday, and I'm going to, I'm going to connect to a local instance I have running here. Maybe if I don't lock myself out. Okay, so we're on my local instance here. I'm creating a table called Big Table. It's got a clustered index on it on column 1. All this table has is some big int columns in it. Column 1 is an identity column here. This is a query I'm using to just insert 10,000 records into the table. So let's do this. So this will, when I'm all done here, it'll populate the table with our data. All right, looks like it's done. So now we're going to use some, I don't know if these are documented now. I haven't looked in a while, but I know for a while these two dbcc commands were not documented, as in you cannot look up documentation on them. But dbcc ind will show you all of the index pages associated with a table. So we've got our table called Big Table, database called SQL Saturday, and we're looking at index number 1, which is right here. Index number 1 is always going to be your clustered index. Any indexes after that, 2 and up, are going to be non-clustered indexes. If you ever see index ID 0, it's because it's a heap and it doesn't have a clustered index on it. So dbcc ind, we're looking at our clustered index, which is index number 1. So this is showing us the pages that are associated with this index. So we've got an IM page, which is the index allocation map. And remember, that tells us what page numbers, page IDs we're looking at that are being used, for this index. We've got different levels here. So we've got level 1 and level 0. Level 0 is always your leaf level, if you think about that diagram that I had in the beginning of the presentation. And then level 1 in this case is the root. This index, because the data is not that large, does not have an intermediate level. It just has a root and leaf. If there was an intermediate level, the intermediate level would be 2, or sorry, the intermediate level would be 1 and the root level would be 2. So as the index gets bigger, the index level goes up and the root is always the highest number. So in this case here, we'll check out the root page. The root page, page type 2 here, is page 328. So we're using dbcc page to look at the SQL Saturday database, file ID number 1, page 328. The number 3 here at the end is just controlling what the output looks like. I don't know what the other numbers do. I always use 3. And then with table results, just puts it into a nice table so we can look at it. All right, so we looked at page 328, which is the root page. We've got 2 result sets here. The top result set is just some metadata. So if we look here, we've got the object ID. So this is the object ID of the table, and then the index ID. The root page, since there can only be one of them, there is no next or previous page because it's just a single page. Here's the type, which is 2, which is one of the root pages here. And then there's just some other information about the records and the slots that they fit into on this index. Where it gets interesting here, though, is the actual contents of the page. This is what is actually stored on the page. So as you can see, it's got the file that the page is on, the page ID, the row number, the level, child field, I'm not sure what that is. I've never, oh no, it's child, sorry, that's child file ID. I'm not sure how that's used. I've never used it before. But we do have a child page ID. This is kind of neat. What this does is this is the linking between pages. So we're looking at the root page right now. It's telling me that for anything that has 246 through 491, we're going to be going to page 336 for that, because this column 1 here is the actual clustered index key. So anything that's got an ID of 491 through 736, we go to 337 for that. And then 736 through 981, we go to 338. So we'll go take a look at that page really quick and illustrate that further. But if we look at page 338, we should see all records that start with 736 and then all the way to 980, because it won't include 981. So let's go take a look at that page real quick here. So data pages, the leaf level pages are presented a little differently. They don't have the 2 table result set that the other one did. It just kind of dumps it here. But again, we've got our object ID, the index ID, and then we've got the previous and next pages. So 337 was the page before this, 339 is the page after. The reason it keeps track of this information is because it allows SQL to do a lot more efficient scans of ranges of pages if it needs to. It doesn't have to keep going up to the root or intermediate page to see which page is next. It can just look right here and see which page is next and scan over to the next page. So if you're doing any sort of range scanning or anything, it uses these next and previous pages to figure out which pages to go to. But if we scroll down further, we'll start seeing the actual table data. So here's our 3 columns of data. Just as the root page showed, this page starts with the record that has an ID of 736. And it should end with something that's less than 981. So if we scroll all the way down to the bottom, we're down here at 980. So this is the last record on the page. So again, just to look at that.
You have a quick question.
Yeah.
Can you please elaborate what is a clustered index key? And also, does page ID need to be unique?
Yeah. So page ID you have no control over. It is unique. It is the actual page of data that SQL allocated to store the information. So SQL handles that. The page ID will be unique to the file that it is on. I guess I should say that much, if that was your question. So if there was 2 files behind this database, file ID 1 and 2 would have page IDs that overlap. But whenever SQL is referencing a page, it also knows what file to look for that page on. So what is a clustered key? So when you're creating a table and you're creating a clustered index, so like if you're creating a clustered index on this table, what you put here is the clustered key. So if, for example, we wanted to have column 1 and column 2 be the clustered key for this table, we'd put it in there like that. So the clustered index key is how the data is sorted in the actual table. And typically it's going to be the most unique value in the table. And we'll talk a little bit about this as well when we get a little farther into the talk here about how you make good choices about the clustered key and why that's important. All right, so we looked at the root page. We saw that page 338 should have started with 736 and ended with 980, which we went and looked at that page and it did. So that's kind of a quick view of the internals. Are there any other questions about anything that we just saw?
Not so far.
All right. I will say too that it feels like we're going to run out of time. That's because we are. This presentation is broken into 3 parts. I only ever get through the first 2. The last part is there just in case people don't have questions, but this is indexing, so people always have questions. There's a quick,
yeah.
I just saw that. Yes, index. Yes, statistics are created for an index when you create an index. I used to talk about statistics in this presentation, but there's so much other stuff to talk about that I don't really discuss it anymore. All right. So we're going to move on to non-clustered indexes, and we're going to come back to these to clustered indexes as well in a little bit here. So non-clustered indexes, when you look at the structure of a non-clustered index, it contains the index key that you define on the root and intermediate pages. If you use included columns, those are on the leaf pages. We're going to talk about included columns in a little bit too. If it's a unique, and these next two items are really kind of confusing. They're important to know, but not important to memorize. If you're creating a unique non-clustered index and a clustered index exists, the clustering key, so in the example that we just looked at, how that column 1 was a clustering key, it's added as an included column to your non-clustered index. If you're creating a non-unique non-clustered index and you've got a clustered index on the table, the clustering key is added to the non-clustered key. And if the table is a heap, the leaf pages of the non-clustered index will include row ID pointers. I know somebody asked about row IDs. A row ID, when you don't have a clustered index, a row ID is an internal mechanism SQL uses to find the pages it needs to. And it's a combination of the page ID, the file ID, the page ID, and then the slot on that page. Pages are broken into slots that the data is stored in. So yeah, the row ID is the page, or sorry, the file, the page, and the slot that the data lives on. So I'll give you a quick example of the same lookup that we did before. Remember, we looked up index 1 or ID number 126 and we found Beyonce at the bottom there. Now we're going to look up by Beyonce's name and find her ID using a non-clustered index. So as you can see, the non-clustered index is a little bit different here. Instead of having the ID and a page number, it has names. I wouldn't recommend typically setting up a non-clustered index on someone's name, but it works well in this example. So here, alphabetically, names between Anne with one N, don't know why I did that, and baby would be on page 2. Baby and cat would be on page 3, cat and Dave on page 4, and so on and so forth. So in this case, we're looking for Beyonce. She's going to be in between these two names, so she's going to be on page 3. And then her name is going to be between Betsy and Bert, so we're going to head over to page 12, and then we find her here. Now, the interesting thing here is that since we have a clustered index on this table, and the clustered index is on the ID of the person, or in this case, the 126, when we look at the leaf level of the non-clustered index, it has the clustered index key on there, or in this case, the 126. Why SQL does this is so that if your query uses this index, this non-clustered index, but it needs more than just the name, like if it wanted to get Beyonce's age as well, it would find Beyonce in this list, it would see that her ID is 126, and then it would use this number to do a lookup on the clustered index for ID 126 to retrieve that age. So this is the clustered index key is always included in the non-clustered index so that SQL knows how to get back to the clustered index in case it needs to get more data.
You have a quick question. For a non-clustered index, is there a maximum number of columns that should be included? For example, if the table has 20 columns, is there a maximum that should be used?
You guys are asking awesome questions that people don't usually ask till later. There's not a maximum number that you can include. There's probably a maximum number you should include. And I will discuss that pretty shortly here, actually. Yes, when I get to general design considerations, we're gonna kind of review some of this and it'll make a little bit more sense. All right, so let's take a look at the non-clustered indexes and see how they are a little different. So if you remembered when we looked at the clustered index, the root page had the clustered index key, which was column 1 on it. And then when you got down to the leaf level, it had every column on it. Column 1, 2, and 3 were all on that leaf level. All right, so if we're gonna take a look and see how non-clustered indexes are a little bit different here. All right, again, I'm just going to be creating some test data. The same table definition: 3 columns, 3 indexes, 2 non-clustered and 1 clustered index. Insert some data here. Okay, we're all good there. I'm going to be looking at the sys indexes table in this case here to get a quick list of the indexes on this table. I don't know why this is called big heap, but ignore that. So on my big table, I've got 3 indexes. I've got a clustered index with an index ID of 1. I've got a non-unique non-clustered index with ID of 2, and a unique non-clustered index with ID of 3. So if we look at our index definitions here, the clustered index is on column 1, the unique non-clustered index is on column 2, and then we've also got another non-clustered index on column 3. So let's take a quick look at, we're going to look at index ID number 3, which is the one on column 2. So this is a unique non-clustered index. All right, so we've got index level of 1 here, which is our root page. This also has an IM page, just like any index would. You know, I don't usually show this until a little bit later, but let's take a quick look at the IM page while we're here. If you look at this really quick, see how this index it's made of pages 448 through 490. If we go and look at the IM page, we scroll all the way down to the bottom. This lists the extents that are used in this index, and you can see that 448 through 488 are allocated for this index, which lines up with 448 through 488. That's the beginning number of the extent. So there's 5 more pages beyond this that you can't see, but that's what the IM page does, is it tells SQL which pages it's dealing with. But anyways, back to this guy here. So this is our root page for the non-clustered index. It's 456. Oops.
Quick question real quick.
Yeah.
What if there were several rows with the name Beyonce, enough rows to not fit on a single index leaf level page? Then there would be several upper level pages with borderline values of Beyonce. Is that correct?
Man, that is a good question. So I don't know. I might have to add that to this presentation, because that's an excellent question. So what you're asking is if your non-clustered index was on the name like it was, and you had tons of Beyoncés for some reason. So I'm thinking what you would probably end up with is you would still have the same intermediate level page. Actually, no, that wouldn't work either. I'll have to test that. I'm not sure. You might end up with a case where the intermediate page would list Beyonce multiple times. That doesn't really seem correct either. Yeah, that I'm not sure. I would have to check on that. At the end of this, there will be a slide that's got my email address on it. I'm also going to write the question down, but definitely feel free to email me directly about it, because yeah, that's something I'm not sure of off the top of my head here. All right, so we're looking at the root page of the non-clustered index here. It looks a lot like the root page of the other. It's got the object ID. There's no previous or next page because we're at the root. It's got the index ID of 3. So if we look down at the data here, we have column 2 listed here. So very much like the other one, page ID 464 contains a column, the records with the column 2 value between these two, and so on and so forth, just like our other index was. Now, if we look at one of these pages, 464, This is the part that you need to really pay attention to, and one of the things that I try to really drive home during this presentation. We've got our column 2 here that our index was created on, but we also have the column 1. Why this is important. So this is the clustered index key. Like I had said, it gets tacked on to the non-clustered index at the leaf level for this specific index here. So if you have a really large clustered index key, that's maybe you decided to create it on 5 or 6 columns. It's made of some really large data types. Whatever you chose for that clustered index key, it has to be repeated at the leaf level of every single non-clustered index you have. So if you have one clustered index with 5 columns that are 20 bytes wide in total, and then you've got a ton of non-clustered indexes, every single non-clustered index record is going to be increased in size by 20 bytes to accommodate for that large clustered index key. So what you may think is a small non-clustered index, maybe you're just creating it on an integer or a big int. Like a big int is 8 bytes. But if you add this 20 byte clustered index key to it, suddenly it's 28 bytes, which is large. When you have more and when the key is larger and larger like that, the combination of these two values here, the bigger this is, the less records you can fit on a page, and the more pages you need to store the data. Whenever SQL does any kind of operation, be it an insert, an update, a delete, it has to read these pages from disk into memory if they're not already in memory, and it does all of its work in memory. It doesn't do anything directly on disk when you're altering data. It always does it in memory, and then puts it into the log and flushes it to disk, and then your transaction is committed. But the important part is that the data is always read into memory. So the larger these indexes get, like if you have a large clustered index key that's getting added to all of your non-clustered indexes, that's more and more data that has to be read into memory, even to do the simplest operations. So if you thought that you were just going to be doing a simple select on a single record that's super narrow using your tiny little index, it might have to read in a lot more data than you thought it would. One reason this can be detrimental to performance is because, oh, excuse me. Sorry, my mouth is drying out here, but as you read more and more pages, not only does it put a lot of pressure on memory because you've only got so much memory to store these pages in, but the more pages you read in, the more work the CPU has to do to actually look at those pages and look the data up. So I hope that makes sense and why it's important to keep your clustered index key narrow, just because based on these these pages that we're looking at here, if it's really wide, it's going to look really bad in here. It's going to have a lot of columns on it, and the size of the row is going to get a lot bigger than you might think it would. And I'll repeat this about 400 more times, so it should make sense when I'm all done here. But so back to this index here. We are looking at index number 3, which was this one here. That was a unique non-clustered index. So in the case of the unique non-clustered index, those columns were added onto the end, at the leaf level. For our other index that we had, which is a non-unique non-clustered index, it's going to look a little bit different. So the same as the other ones, your root level is here at 1, your leaf level is at 0. If we look at the root page, which is on 408, this is where things get a little bit crazy. So here, even though this index was only created using column 3, you can see here at the root level that column 1 is included. Since column 1 is included, suddenly, in this case, your root page can only store half as much data. And then all of your intermediate pages can also only reference half as many pages because they have to store more data per page. So the height of your index, the depth of it, can grow considerably when you have a large clustered index. In this case, it's not a large clustered index key because it's just on the one column. But if this was on multiple columns, every column that you added here is less and less data that root page can store, and more pages that have to be read. Also to Anthony Freeman, never apologize for questions. And to your question about the GUID, we'll talk about that in a little bit as well.
Yeah, I'm making a list of a few questions that will come at that time. So.
Okay, cool. All right, so this was our root page right at page 408. So let's take a look at one of these leaf pages. Again, it's going to look a lot like the other ones did. And here, again, we've got that clustered index key showing up, tacked right onto the key itself. This is for a demo in a little bit. All right, might have to have a one-on-one here with Anthony. That's a good question, and we're going to talk about that too. He's asking why should you use multiple columns in a clustered index? We're going to talk about something called surrogate keys and natural keys, which will make that make a lot more sense. All right, so that was non-clustered indexes. We've also got something called a heap. A heap is simply a table without a clustered index. If you remember, a clustered index physically sorts the data. It puts the pages right next to each other. A heap is the opposite of that. The best analogy I've heard of for a heap is if you had one of those old school like CD binders where you can fit like 4 CDs per page, and you had it all nice and alphabetized. That's a clustered index. If you were to tear all the pages out of your CD binder and toss them on the floor and mix them up, that's a heap. The only way you're going to find what you're needing is to look at every single one of those pages to get the data that you need. And that's kind of how heaps operate. So as I just implied by the analogy here, heaps are unsorted and completely unstructured. It is literally a heap of pages. There's no root pages, there's no intermediate pages, just the IM page. So if you remember the IM pages, it lists the the extents that are owned by an index. In this case, SQL really has no option if you have no indexes on the table other than to look at that IM page, say, oh, okay, I see we've got these 10 extents involved in this heap. I just have to read all of them now, and it will go and look at all of those pages, even if it only needs data from one of them. So heaps can be pretty terrible. There's a lot of arguments around using heaps for high performance inserts. There's also articles that say that they don't perform well for inserts. My general opinion on heaps is don't use them unless you absolutely know that you have to. And test. But for the most part, it's a good idea to have a clustered index on any tables that you create.
You have a couple questions. So to confirm, sorry, a non-unique, non-clustered index includes the cluster key on both the page and the leaf. Is that correct?
I get these mixed up all the time. I put the slide back up, but the important thing to remember, even if you don't remember, what the difference between the unique and non-unique is that when you've got a really wide clustered index key, it makes your non-clustered indexes a lot bigger. That's the most important thing to remember about that. But here's the slide that talks about that as well. So yeah, the unique, if there's a clustered index on the table, you create a unique non-clustered index. The clustered key is added as an included column, so that'll just show up on the leaf level. And then non-unique, it will actually add it to the key. So it'll be like you created the non-clustered index on multiple columns, even if you only created it on one.
And then a second question, how does the index work for the non-in-row data, such as a lob?
So that data is index work for the non-row data, such as lob. You can't create a clustered index on a lob. I don't think you can create a non-clustered index on a lob either. You can use full text. You can use full text searching on lobs, but I don't think that you can use just standard indexes. There is a limit on the size of the key that you can use for any index. I can't remember what it is off the top of my head, and I believe it's changed recently. But there is a limit to the key size. All right, we'll do a quick look at heap structure, and then looks like we might run out of time. But and then we'll talk about some design considerations here. All right, so heap structure will be quick. Again, creating a big table, not putting any indexes on it. We're going to look at the pages related to index 0, which, if you remember, that means it's a heap. If it has an index 0, that's a heap. So as you can see, we've got an IM page, and then that's it. There's no index levels. There's nothing to differentiate these pages from each other. And the really kind of terrible thing about this is that if you look at one of these data pages, there is also no linking between pages. So there's absolutely no way for SQL to navigate this other than to read all of the data. That's really the only option if all you have on a table is a heap. You can possibly get away with a heap and a non-clustered index as long as all of your queries hit the non-clustered index. But I would typically just recommend testing it with a clustered index before you try to do something like a heap with a non-clustered index. DBCC IND will not show index fragmentation. I just saw that.
And I got the last question.
Okay. All right, so those are the demos. I don't spend a lot of time on heaps because I feel like in most situations there's not a good use case for them. If there is a use case for you, awesome. But just make sure and test a lot. All right, so this is the part of the presentation where I kind of tie a lot of stuff together. So clustered indexes, we want to keep the key narrow, both in data size and column count. You want to try to pick something sequential that doesn't change. Back to the CD wallet analogy, the reason that you want to create something sequential that doesn't change is because imagine if you had like a 300-page CD wallet, if such a thing existed. And you just got a new album, super excited to put it in your new wallet, but the page that it belongs on is in the middle because you've got it in alphabetical order. And the only way to fit that page into the middle would be to add another page and then take half the records from the current page, put them on that new page along with your new album, and then leave the others on the page they were on. That's kind of what SQL will do if you do not have a sequential clustered index key. It has to, when new records come in during an insert, if the clustered index key is not sequential, it'll have to kind of cram it into the middle of everything, which can lead to fragmentation. Fragmentation being when there's a lot of empty space on your pages because pages had to be split or other things happen that cause things to not be able to fill up the pages all the way. But you also want to try to pick something unique. The interesting thing about this is if you pick something, if you choose to create a non-unique clustered index, which you can do that, it is an option, SQL will make it unique anyways in the background. So when you're using like the DBCC page to look at a non-unique clustered index, it just adds another column basically to your table called the uniqueifier. And if there's values in your index that are not unique, it will just tack an extra value on it to make it unique so that SQL has a way to look it up. So there's not really a lot of reasons I could see to create non-unique clustered indexes. So just make sure that when you're creating your clustered indexes, they're on something unique. Again, with the CD wallet thing, try to pick something fairly static that's not going to change a lot. If you pick something that changes, data is going to have to be moved around, which can lead to a lot of empty space on pages. Empty space is bad because you'll have to read more pages to get the job done. Don't fear surrogate keys with clustered indexes. A surrogate key is a key that you make up to fit the data. So there's surrogate keys and natural keys. A natural key would be a number that is always going to be unique in a data set. For example, if you had a list of people and their social security numbers, assuming none of those numbers have been reused, the social security number might be a good, a natural key. With GDPR rules, obviously you don't want to do that, but a social security number could really be a good natural key for people. That's what we call, a natural key. There's something in the data that is unique and relatively small. If you have to go out 4 or 5 columns wide before you can find something unique that identifies each row, then it might be time for a surrogate key. And what I mean by surrogate key is maybe you just add an int column to the table that increments by 1 every time you insert a record. That's always going to be sequential. It's always going to be unique. You don't have to worry about fragmentation issues and stuff as much, unless you're deleting a lot of data. But yeah, so surrogate keys can be useful if your data is not naturally uniquely identifiable. I do say you should fear the GUID because GUIDs are random and they're large. And again, as we know now, a large index, clustered index, will lead to larger non-clustered indexes, which can cause memory and CPU issues. So try to not use GUIDs unless you absolutely have to. There are use cases for the GUID in indexes, but it's way more advanced than what I want to talk about in this session here. But for the most part, try not to use them.
Real quick, what about sequential GUIDs?
Sequential GUIDs, you can use them. I don't see a reason to, because a big int will give you just as many possibilities as far as your values go, with much narrower data size. If you're gonna go with sequential GUIDs, it would almost just make more sense to use an identity column that's like a big int or something like that. All right. So non-clustered indexes, some of the same stuff. You want to keep the key as narrow as possible. The key columns should be in the order of selectivity. What that means is if you're using 3 or 4 columns in your non-clustered index key, the order that you add the columns to the index should be in the order of how unique they are. Also, when using non-clustered indexes, you want to take advantage of included columns. So if you've got a query that selects 3 values from a table, 3 columns from a table, and there's 1 or 2 columns in the where clause, you would add those where clause columns into your index key, and then the columns that it's going to be selecting, you would add those into the include. What that does is creates a covering index. So when you run that query, SQL will only use that non-clustered index and will not have to go back to the clustered index for any reason. That's typically your goal when you're creating non-clustered indexes, is trying to create an index that encompasses all of the data you need for a query. You'll have to balance that. There was a question earlier about how many included columns can you have. If you're including like 60% of the columns in the table, you might want to take a step back and think about what you're doing there. In that case, it might be cheaper to just let SQL use the non-clustered index to find the records it needs and then refer back to the clustered index to get the rest of the data. But that's again something that you'll have to test, and it's going to depend on your use case. A few questions stacking up here. One more thing I want to say in here, and then we can go to those. 2 more things. You want to index your foreign key columns. So if you've got foreign key relationships between 2 tables, you just want to make sure that those columns that there's a non-clustered index created on them, if possible. And then also remember that the clustered key columns are free. So any non-clustered index you create, the clustered key values are always going to be part of that index, so you never have to manually add them to the index.
Okay, question, is the GUID unique for one SQL server, or is it unique universally?
A GUID should be unique universally. Sequential GUIDs, I think, are as well. The GUID uses a combination of things on the actual server itself to get its uniqueness. So yeah, a GUID should safely be unique.
Let's see. Should the index key be in order of the where condition? That's a good one. That's a good question.
It should not. It needs to be in the order of how unique things are. So again, if you've got a table of people, if you're looking for people with a first name of Mark and a social security number of my social security number, you would not create the clustered index or the non-clustered index starting with Mark. You would create it starting with the social security number, because that's going to be less steps and less pages to scan through to find the data that it needs. So you always want to create them in the order of how unique the columns are.
And then would you ever want to add the primary key column as part of the index and or included column?
That's what I meant when I said that those columns are free. They're automatically added to the index, to the non-clustered indexes, so you don't have to put them in there. Now, there might be cases where you might want to do a combination of one column and then another column from your primary key. If you've got 3 columns in your primary key, or in your clustered index rather, and you do a lot of querying on the second column, it might be okay to create a non-clustered index on that column. But if you don't care what the if you're never using those 3 columns in your where clause, but you just need to return that data, then you don't have to add them. They'll already be there. I hope that answers the question.
Perfect.
All there. All right, some general stuff for all indexes. You want to lead with the most selective predicate for the workload. So again, the most unique value possible. You always want to lead with that. If the lead column of an index is not in the query predicate, so if it's not in the where clause, it's not in a join clause, the index will not be used unless it is 100% covering. So what that means is if you've got a bunch of queries that all they have in the where clause is like a date, but you don't have any indexes that lead with date, it's not going to use any of those indexes. Now, if you've got an index that leads with, column 1 and 2 and includes the date, and that covers all of the columns needed for your query, SQL could decide to use that index, but it probably won't be that efficient because it's more than likely going to have to scan the whole index. So you typically want to lead your indexes with the most unique column that's being used in your workload. Another important thing, just nothing technical about this, but analyze current index usage before creating new ones. There's so many times I've looked at a table, there's like 13 indexes on them. There's 5 of them that start with the same column, and most of those can be compressed into one single index. So always take a look and see if maybe there's an index you can just modify before you start creating new ones. In general, the wider the column, the slower the index. So always keep that in mind. And again, with the clustered index, the wider that column is, or if you're using multiple columns, the slower all of your indexes are going to be, because there's going to be more pages needed to store that data. Also, don't forget your join predicates. So if you're joining multiple tables together, those join conditions that you're using for your joins, those can be indexed. So don't forget to index those. Those can that can actually speed things up quite a bit. General rules of thumb: write-heavy workloads will benefit from fewer indexes, and read-heavy workloads will benefit from more indexes. One more thing, and then I'll answer a couple questions. All right. The simple goal for all indexing is to reduce I/O. If anybody has not used it before, this is an amazing command: set statistics I/O on. You can use this when running queries to see how many pages SQL had to read to get the data. An index read always starts by reading the IM page and ends at the leaf. So you're always going to have at least those 2 in there. More I/O is more pages in memory, more pages for the CPU to juggle. Less I/O typically means more speed. I had a little sample here in our heap demo where no, I didn't. It was in this one where I turned that on. So set statistics IO on. Let me get back into my table here. Got to regenerate my data apparently. All right, so we've got set statistics IO turned on. We do a select from the table here, and here's the message that comes out. And this is really good information to know. So logical reads, that means that in order to get this no data here that we're seeing, it had to read through 20,664 pages. If you do some quick math, so it's a 20,064, there's 128 pages per megabyte. So it had to read through 161 megabytes of data to run that query that I just ran there. It also tracks physical reads. So if you're having memory pressure or this query just needs so many pages that that memory is exhausted, it'll actually start hitting the disk and you'll see physical reads start to go up. So this alone, set statistics IO, is a fantastic way to performance tune and see how your indexes are doing. So you could run this query, check out your logical reads, create an index, run it again, and see what your logical reads are. If they go way down, then the query should run faster and consume less resources. All right. The rest of this is all kind of anti-patterns and stuff, and most of it can be understood by just looking at the slides. So we can go ahead and go into some of these questions here.
Okay, two of them about dates and or timestamps. Are dates bad to use in an index? And then pros and cons for indexes on timestamps since they're not the most narrow.
So again, you want to try to keep things as narrow as possible. Sometimes it's not possible, right? So you just have to index on what you can. As far as dates go, dates are fine to index by if you know the date is not going to change and the date is always going to be kind of ever increasing. So if you're tracking like sensor data might be a good example where
You still with us?
I bumped the mute button. So I don't know what everybody heard, but as far as indexing by dates, we'll use an example of reading temperature from a sensor. If you're tracking temperature data and you've got some dates and you're just doing inserts, and every time you do an insert, the date is the date of right now, indexing on that date would make sense. Where you can kind of fall into trouble with that is that if you need to query on the last 30 seconds of data, the stats might not be up to date enough to come up with a good query plan. So you could run into some performance issues there, but for the most part, like with any other type of column, if your dates are sequential and they don't change, and they're used in a lot of your queries, then it could be good to use. It could be good to index that date. Now, would you want to do a clustered index on that date? I don't know. It depends on the number of rows and what your workload looks like.
All right, and one more question, and then we'll go ahead and finish off. Do you prefer Operations Manager over SSMS?
Funny story. I always do all of my demos on a Linux laptop, but I could not get it working with GoToMeeting, so I'm just used to using the the Operations Studio, now called Azure Data Studio. That's the only reason I'm using it is because it's what I'm used to using when I do presentations. It's got a few things I don't like about it. It's not good when you're querying really large data sets because the result grid doesn't handle it very well. But overall, it's a really nice product.
Wonderful. All right, before I say thank you, I wanted to give you guys time to, if you have any more questions or want me to pass your email to the speaker, please indicate that in the questions panel. I know some of you have asked questions and I've tried to answer a few while he's also been answering as well, and I am not able to pass your email to him without your approval. So please indicate that in the questions for me. I also, this will be recorded, so you will actually have this on dbafundtube.org within the day or so. Thank you very much, Mark. It was an absolutely wonderful presentation. I do love.
Thank you.
I always pick up something when I'm learning, listening to something about indexes. So
I've got this slide at the end here too with all of my contact information on it.
wonderful.
Feel free to email me directly anytime. I'm always open to answering questions. I'm taking a little break from social media, so maybe don't tweet me right now, but you can always hit me up on email, and I'll be there.
Also, for anybody who's interested in the information, the demos and such like that, again, this is going to be recorded, but also I saw on the SQL Saturday Charlotte, October 20th, he gave this session at that time too. So you can, and he has a zip file that you can go ahead and download as well. So.
Yes.
All right, so make sure you check out our contact information and upcoming meetings at dbafund.org. We have a couple more this year, and we've already been lining up next year. So check them out. You'll also get an email from us if you sign up through the PATH website with all of those sessions as well. Again, all of our next meetings are there. You'll also see our YouTube recordings at dbafundtube.org. This one will be soon, and they're always posted within a day or so of other presentations. So thank you very, very much, everyone. Have a great day and see you guys soon.
Great job, guys. I'll end it.